Okay. In the previous discussion, we had seen the three-phase fault calculation at bus bar 3 fault current and line to ground fault current. Line to ground of this V3A naught. I'm assuming the line to ground fault is occurred between phase A and ground. We have also did a small correction in the zero sequence reactance diagram by including the transformer connections. There is also one more correction in this, that is in the question if we observe they have given the neutral grounding reactance of generator 1 and generator 2 is 0.25 by 3 per unit. Here directly they have given in per unit. In case if they had not given in per unit, then we should find the per unit value. This actually, if you observe till now, we didn't include this neutral grounding reactance Zn, which is 0.25 by 3 in our problem. So this Zn should be included in the zero sequence reactance diagram, but we missed it. So to avoid confusion, till now whatever we have followed, that is Zn equal to 0. So let us solve the problem by considering Zn equal to 0. But let us also see what we need to do when they had given Zn. Suppose if they had given, instead of giving per unit, they had given the neutral grounding reactance or neutral grounding resistance is 3 ohm. 3 ohm. So it is actual value. Then you need to find base value, which is equal to kV square by MVA. Then actual by base will give the per unit value of the neutral grounding reactance. Now where to include this neutral grounding reactance? As transformer connections are included only in the zero sequence diagram. Similarly, this neutral grounding reactance also included in the zero sequence reactance diagram only. So the effect of neutral grounding reactance Zn. Zn where it will be included is Z not equal to Zs plus 3Zn. What is this Z not and Zs? Zs is nothing but per unit value of the generator, which we have calculated by considering old per unit value as x naught, that is 0.05 for generator 1 and generator 2. The change we need to do when they give grounding reactance is we need to include 3 Zn in series with Zs. That is, along with the per unit value we have calculated new per unit value, we need to include the 3 Zn in series with the generator reactance diagram. In the generator reactance diagram, along with the new per unit reactance, we need to include the 3 times the neutral grounding reactance, 3 into 0.25 by 3 in series with Zs or reactance, new per unit reactance for generator 1 and generator 2. This is the only change. Then in the question, if they had given solidly grounded, then you can take Zn equal to 0. They will tell generator 1 with a winding connection of star with neutral grounded is solidly grounded, and they will give MVA and kV ratings old per unit value. Solidly grounded means Zn equal to 0. Similarly, if they had asked us to find bolted fault, if you see this problem, in this problem what they had told, they had given that find the three-phase fault with ZF. Fault impedance is J.1. Suppose if they had asked to find the three-phase bolted fault at bus bar 3, then the fault impedance is 0. Bolted fault means fault impedance is 0. Then what is the leftover? We have line to line fault. For this, for that, first we will find the sequence components of the current. The sequence components will be zero sequence component will be 0, positive sequence component equal to minus of negative sequence component, which is equal to this formula V3A naught by XTH1 plus XTH2 plus ZF. Then from that we can find the phase components of fault current I3 using the same matrix relation. Then the last fault is the LLG fault, double line to ground fault. Here line to line fault, I am assuming it is happening between phase B and phase C or line B and line C. Then coming to double line to ground fault. In double line to ground fault, as usual, first we need to find the sequence components. In sequence components, first we need to find positive sequence component. That is very important. I31 we need to find out, which is a pre-fault voltage divided by Thevenin's equivalent for positive sequence plus Thevenin's equivalent for negative sequence in parallel with Thevenin's equivalent of zero sequence plus ZF. So this is the, you can remember this. Since these two are in parallel, it will be R1 R2 by R1 plus R2. So this is the complex formula. Why we need to first find out this positive sequence alone? Why? Because negative and the zero sequence formulas having the positive sequence included in them. If you want to find the negative sequence, you should know the positive sequence first. Similarly, if you want to find zero sequence, you should know this positive sequence current first. Again, after finding the positive, negative, zero sequence, using this matrix, we can find the phase sequences of I3, phase components of the fault current. So with this, we will end this problem where we have calculated for unsymmetrical three types of faults, we have calculated sequence components and phase components of currents. For symmetrical fault or three phase fault, we have calculated the fault current. Thank you.